I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about extrinsic semiconductors and the carrier concentration in extrinsic semiconductors. Now, if we look into the module 2, we have discussed all these topics: the free electron theory, Bloch theorem, chronic penny model, and classification of materials. And in my last two lectures, I have discussed in detail about the intrinsic semiconductors. And in this lecture, we are going to discuss about the extrinsic semiconductors. And then we will derive expression for the carrier concentration also. Now, the brief outline how we are going to discuss this topic. First, we will see what are extrinsic semiconductors, and then we will see the classification of N-type semiconductor, and then we also have P-type semiconductor. So, we will discuss about N-type, P-type. Then we will derive the expression for Fermi level, and then we will derive the expression for carrier concentration. Now, let us see the classification. Semiconductors can be broadly classified into intrinsic semiconductors, which are pure semiconductors. We have seen the examples germanium and silicon. We have already discussed about these intrinsic semiconductors in our last lecture. So, in this lecture, we will be talking about extrinsic semiconductors. So, what are extrinsic semiconductors? They are impure semiconductors. Extrinsic semiconductors are impure. Impure means what? When we take a semiconductor, for maybe germanium or silicon, you take and you add some other atoms of a different element, then it becomes impure. Suppose I take silicon. If I take a silicon crystal, all the atoms are arranged in a systematic fashion. But if I add another element or a few atoms of another element, these atoms are going to replace the silicon atoms. Then it becomes impure. So, depending upon the type of impurity we are adding, it will become either an N-type or P-type. So, extrinsic semiconductors can now be classified as N-type and P-type. So, how do we get N-type semiconductor? So, we get N-type semiconductors by adding pentavalent impurity. So, what is this pentavalent impurity? The name itself says penta means 5. So, any impurity or any atom which has 5 valence electrons, if we are adding to a semiconductor, then it becomes N-type. If I say pentavalent means it will have 5 valence electrons. Valence electrons means electrons which are present in the outermost orbit. Now, if there are 5 electrons, we are calling it as pentavalent impurity. Now, when we add a pentavalent impurity like phosphorus, arsenic and antimony, all these belong to the 5th group. If we see in the periodic table, all 5th group elements will have 5 valence electrons. So, when we add a pentavalent impurity, what happens is it becomes a donor impurity. Why it is a donor impurity? If you are talking about a semiconductor has 4 valence electrons. It has 4 valence electrons. If I take silicon, it has 4 valence electrons. Now we are adding a pentavalent impurity with 5 electrons. So total 5 plus 4, we are getting 9 electrons. And we all know for stable configuration, we need 8 electrons in the outermost orbit. So, 1 electron is always free. It is ready to donate that electron. So, we are calling it as a donor impurity, and the concentration is denoted by Nd. And if you see in donor impurity, Ne means the concentration of electrons is more or much higher than the concentration of holes. This is what we need to understand about N-type. N-type is obtained by adding a pentavalent impurity. Examples are the fifth group elements phosphorus, arsenic, antimony. By adding this, it becomes a donor impurity because it is having one extra electron, and always the number of electrons is greater than the number of holes. Now coming to the p-type. So when we add a trivalent impurity. So what is a trivalent impurity? If we are talking about trivalent impurity, means it will have trivalent. Tri means 3. So it will have 3 valence electrons. So they belong to the third group. Whenever we are adding an impurity from the third group, examples, gallium, boron, indium, aluminium, whenever we add impurities having 3 valence electrons, then it becomes a trivalent impurity. And when we are adding a trivalent impurity to a semiconductor which has 4 valence electrons. Now, what are the total number of electrons? From the trivalent impurity, we are getting 3, and the semiconductor has 4 valence electrons. So, total there are 7 electrons, and for stable configuration, we need 8 electrons. So, what does this mean? This is always ready to accept 1 electron. So, we call it as acceptor impurity. So, you need to understand why we are calling it as an acceptor impurity, because to attain stable configuration, it is having a deficiency of 1 electron, and so it is always ready to accept 1 electron. So, by adding 1 electron, it becomes stable. So, we are calling it as a acceptor impurity, and the concentration is denoted by Na, acceptor. And here in this case, the number of holes is always greater than the number of electrons. And when I talk about holes, one thing we need to understand here is a hole is nothing but a deficiency of electron. So whenever we are talking about electrons, wherever there is a deficiency of electron, we call it as hole. Now let us compare intrinsic with extrinsic semiconductors, because we are going to see in detail about extrinsic semiconductors. So it is good to know how extrinsic semiconductors are different from intrinsic semiconductors. Intrinsic semiconductor is in its pure form, means pure. If you are taking a silicon crystal, all the atoms are silicon atoms. But here in extrinsic semiconductor, it is formed by adding a trivalent impurity or a pentavalent impurity. In both the cases, we are calling it as impurity, and it becomes a extrinsic semiconductor. And in case of intrinsic semiconductor, the number of holes is always equal to the number of electrons in intrinsic semiconductor. But if we see in extrinsic semiconductor, number of holes are more in p-type and number of electrons are more in n-type. They are never equal. In case of extrinsic, the number of holes and electrons are not equal. So either the holes are more or the electrons are more. In case of p-type, the holes are more in number. And in case of n-type, the electrons are more in number. Then coming to the Fermi level. Fermi level lies in between the valence band and conduction band. Fermi level is nothing but the highest filled energy level. So here in case of intrinsic semiconductor, it lies exactly in between the valence band and the conduction band. The gap in between the valence band and conduction band, exactly in between that it lies. But when we talk about extrinsic semiconductor, Fermi level lies near the valence band in p-type, and in conduction band it lies near, in n-type it lies near the conduction band. So here the Fermi level, the position of the Fermi level varies with the type of impurity we are adding. When it is an acceptor impurity, the Fermi level is towards the valence band. And when it is a donor impurity, the Fermi level is towards the conduction band. And then the ratio of majority and minority carriers. In this case, because we are saying that the electrons and holes are equal, there is nothing like majority and minority. They are equal. But if we have to compare it with extrinsic, we say the ratio is unity. Because they are equal, so the ratio is always equal to 1. So we call the ratio is unity. But in case of extrinsic, ratio of majority and minority carriers is not unity. It depends upon which are the majority carriers and which are the minority carriers. So if we are talking about N-type, holes are the majority carriers. So Ne upon Nh will be greater than 1. If we are talking about P-type, holes are the majority carriers. So Nh upon Ne will be greater than 1. Now let us look into, first we'll talk about N-type semiconductor. How an N-type semiconductor is formed, how we are talking about the number of electrons that it can donate. So when a pentavalent impurity like antimony or phosphorus or arsenic, all these belong to the fifth group. They are added to pure silicon or germanium. So silicon and germanium are semiconductors. So we are taking a semiconductor like silicon or germanium, and to that we are adding a pentavalent impurity. So pentavalent impurity from the fifth group, that is, we are talking about antimony, phosphorus, arsenic. What happens? 4 of its 5 valence electrons form covalent bonds with its neighboring 4 silicon atoms. So, as I told you, when we are adding an impurity, some of these impurity atoms replace the silicon atoms in the crystal structure. So, these impurity atoms which have 5 valence electrons, now they start forming bonds with the neighboring silicon atoms. So now suppose we have a phosphorus atom here and this is surrounded by 4 silicon atoms. We have many, but I am just showing you 4 silicon atoms. So silicon has 4 valence electrons. So for all the 4 silicon atoms, we can show 4 electrons. Whereas phosphorus is pentavalent, so it will have 5 valence electrons. So 4 plus 5. Now this phosphorus is going to form covalent bond. This is how it forms the bond with the neighboring atoms. So now phosphorus, by forming covalent bonds, it is attaining octet configuration, that is stable configuration, but still this electron is free. So 4 of its 5 electrons, means out of the 5 electrons, valence electrons it possesses, 4 of them are bonding covalent bonds with the neighboring silicon atoms. This is how we have seen. Now the 5th electron of each impurity is loosely held with its parent atom and can be easily detached by supplying a little amount of energy. Now this electron which is not bonded, it is free, or if it has to be removed from the metal, if you supply a little amount of energy, it can be made free. That is what we are trying to understand. What happens after bonding is, with each phosphorus atom we are adding, we are getting 1 free electron. So when we add a number of atoms, so which gives rise to more and more electrons. Now energy levels are introduced to all the 5th electrons of the impurity atoms just below the conduction band. And these levels are called as donor levels, and the impurities added are called donor impurities. Whatever impurity we have added, we are calling it as donor impurity because it is ready to donate 1 electron. Now if we see the energy band diagram for this, how do we see the energy band diagram? we have the valence band, we have the conduction band. There is a small energy gap of the order of 1 electron volt for semiconductors. Now, because of the impurity that is added, there are free electrons, and all these we are calling them as donor electrons, and they lie in a level here very near to the conduction band. And this level we are calling it as donor level. All the free electrons are lying in a level just below the conduction band, and we are calling it as donor level. Now, at room temperature and temperatures very near to the room temperature, all the electrons in the donor level jump to the conduction band because they are lying very near to the conduction band. Even if you supply very little energy, means at room temperature also, what happens? These electrons will move into the conduction band, and then only a very few electrons from the valence band jump to the conduction band. So after all these electrons are shifted into the conduction band, if you are further increasing the energy, some of the electrons from the valence band also may shift to the conduction band. Then in that case, if you compare the number of electrons in the conduction band and the number of holes in the valence band, the number of electrons is very high. That is why we say here Ne is always greater than NH. Because initially the electrons from the donor level are shifting to the conduction band, and then the electrons from valence band are shifting. That is why what we observe here is Ne greater than NH. Now what we are calling here, because Ne is greater than NH, the electrons are called the majority carriers because they are more in number. They are in majority. So we call them as majority charge carriers. So there is a new concept. If you are talking about a conductor, we say only it is conducted due to electrons. But here when we come to semiconductors, there are two types of charge carriers. One is the majority charge carriers, that is the electrons in N-type, and holes are the minority charge carriers. So we are introducing this concept of majority carriers and minority carriers. Why majority? Because they are more in number when compared to the holes. Electrons are more in number. So electrons are the majority carriers and holes are the minority carriers. And as these are excess conducting electrons, the semiconductor thus formed after doping pentavalent impurities to a pure semiconductor, we call it as N-type. So what is this term doping here? We are doping pentavalent impurities. Doping is nothing but the process of addition of an impurity. Doping means it is the process of adding an impurity to a semiconductor. The process of adding an impurity to a semiconductor, we are calling it as doping. So by doping pentavalent impurity, we are getting N-type semiconductor. Now if you see the crystal structure and also the band diagram together, so we have one phosphorus atom replacing silicon here. So after adding a pentavalent impurity like phosphorus, so what is happening here? This phosphorus is forming bonds with the neighboring silicon atoms. After forming bonds, one electron is free. And all these free electrons, if we have to show in the band, energy band diagram, they lie at a level which we call it as a donor level. This is called the donor level. All these free electrons will lie in the donor level, and this donor level lies below the conduction band. So this is the valence band. Valence band means the range of energy is possessed by valence electrons, and conduction band represents the range of energy is possessed by conduction electrons or free electrons. But in this case, what is happening? By addition of an impurity, we are getting extra electrons which are ready to be donated. So we are calling them as donor levels. Now let us see the expression for carrier concentration in N-type. Carrier concentration in N-type. Carrier concentration here means what is the concentration of the charge carriers. First we will talk about N-type. So it will be definitely the electrons. Now let Nd be the donor concentration. Means the number of donor atoms per unit volume we are adding. We call it as donor concentration. I said in doping what we are doing, we are adding an impurity. So if we are adding Nd number of donor atoms per unit volume, so we call that as donor concentration. And Ed is the donor energy level. The energy level that is slightly below the conduction band. Now at room temperature what happens? At 0 temperature they are lying in the, at 0 Kelvin they are lying in the donor level. But at room temperature what happens? The donor level is filled with electrons, and as the temperature increases, these donor atoms get ionized and electrons take transition from the donor level to the conduction band. So with increase in temperature, what is happening? The electrons from the donor level, because the atoms are getting ionized, they are shifting to the conduction band. And because of this, what happens? The density of the electrons in the conduction band increases. More and more number of electrons shifting from the donor level. So the number of electrons per unit volume increases in the conduction band. So the density of electrons in the conduction band increases. So we will be using this expression which we have already derived. So what is the expression for density of electrons in the conduction band? We have already derived in our previous lecture. You can refer to the video for this derivation for this expression. So N here represents the concentration. Concentration of electrons in the conduction band is given by 2 into 2 pi me kBt by h square power 3 by 2 into e power minus of Ec minus Ef by kBt. So what is N here? N is the electron concentration. In conduction band. This is in conduction band. Then Me star represents the effective mass of electron. Me star represents effective mass of electron. And Kb is the Boltzmann constant. T is the temperature. H here is the Planck's constant. Ec represents the lowest energy level in conduction band. Lowest energy level in conduction band. And Ef represents the Fermi level. So we are going to use the same terms in the derivation. So you need to understand what they represent. So N represents 2 into 2 pi me kBt by h square power 3 by 2 e power minus of Ec minus Ef, or we can simply write it as Ef minus Ec by kBt. Now let us see the density of the ionized donors. Means what about the density of the electrons that is coming from the donors, that is given by Nd into 1 minus f of Ed, or simply you can write it as Nd exponential minus of Ef minus Ed by kBt. You need to know only kBt, all the other things we have discussed. So Nd here represents the donor concentration. Definitely, so the number of electrons depends upon the number of donor atoms that are added or that are ionized. So Ed here represents the donor level, energy level of the donor. So we call this as donor level, energy of donor level. So Nd is equal to e power minus of Ef minus Ed by kBt. So we are considering this concentration of electrons in the conduction band as 1, and then the density of the ionized donors which are going to shift into the conduction band, we are writing as Nd into e power minus Ef minus Ed by kBt. This we are representing by equation 2. Now at very low temperatures, the number of electrons in the conduction band must be equal to the number of donor atoms per unit volume. No? So where are we getting the electrons from into the conduction band? From the donor atoms. So at low temperatures, all the atoms whichever are ionized, the electrons corresponding to those atoms are going to the conduction band. So therefore we can say that the number of electrons in the conduction band must be equal to the number of donor atoms per unit volume. So we are going to equate 1 and 2. So from 1 we have 2 into 2 pi me star kBt by h square power 3 by 2 e power minus of Ec minus Ef by kBt is equal to Nd e power minus Ef minus Ed by kBt. This is coming from the donor concentration. Now we are going to simplify these two and we are going to get the Ef. Now if I just rearrange the terms, I can bring this exponential term here onto the left hand side and bring this term onto the right hand side. So what we have here is e power minus Ec plus Ef by kBt, which is there on the left hand side, and in the denominator we are getting e power minus Ef plus Ed by kBt is equal to Nd upon this comes to the denominator, just transposition. So Nd by 2 into 2 pi me kBt by h square power 3 by 2. Now let us simplify these things. Whatever we have in the denominator, because it is the same base, we can take it to the numerator and write it as e power minus Ec plus Ef, because we have minus Ec and Ef. I am bringing this minus Ef also to the numerator. It becomes plus Ef minus Ed. So if you are writing Ef plus Ef, you get 2Ef. Minus Ed and minus Ed, we are taking 1 minus common and writing it as Ec plus Ed by kBt. So this is equal to Nd by 2 into 2 pi me kBt by h square power 3 by 2. This remains as it is. So we have simplified the left hand side. Now we are going to take the logarithm. So if we take the logarithm on both the sides, exponential of log power x is simply x. Exponential, we are taking log e power x. So we get only x. So 2Ef minus Ec plus Ed by kBt is equal to log of Nd by 2 into 2 pi me kBt by h square power 3 by 2. Now we will take kBt onto the other side. We are just taking this denominator to the right hand side. So we have 2Ef minus of Ec plus Ed is equal to kBt log Nd by 2 into 2 pi me kBt by h square power 3 by 2. Now we want to find Ef. Ef is the Fermi level. So we are going to take minus of Ec plus Ed also onto the right hand side. So this minus, if it comes onto the right hand side, it becomes plus. So Ec plus Ed, and this 2 we are getting because we are writing Ef. So I'll write one more term here. 2Ef will be equal to Ec plus Ed. I have just brought this Ec minus Ed onto the right hand side. We have plus kBt log Nd by 2 into 2 pi me kBt by h square power 3 by 2. Now if I want to write Ef, this 2 comes onto the other side, it goes to the denominator. So we get Ec plus Ed by 2 plus kBt by 2 log Nd by 2 into 2 pi me kBt by h square power 3 by 2. So this is what we are getting here, EC plus ED by 2. This is the term. Then KBT by 2 log ND by 2 into 2 pi ME KBT by h square power 3 by 2. This is at a temperature T greater than 0 Kelvin. Now what will happen at T is equal to 0 Kelvin? So if we substitute for T 0, what will happen? This whole term goes to 0 because you have T here. So 0 into something is 0. So we are left with EF is equal to EC plus AD by 2. So what does this mean? EF lies between EC and ED. So what we are trying to understand from this expression at 0 Kelvin, the Fermi level lies in between EC and ED. So if we try to understand the figure, this is how we see. This is the valence band, this is the conduction band, and this is the donor level. Okay, so lowest level we are denoting it by EC, highest level in valence band we are denoting by EV, and now this is the donor level we are denoting by ED. Now what did we get from by deriving the expression we got at T is equal to 0 Kelvin? We are getting EF is equal to EC plus ED by 2. Means EF lies exactly in between EC and ED. So where will our Fermi level lie now? This will be the Fermi level. So this is what we are trying to understand. The position of the Fermi level matters a lot in semiconductors because this is with the help of this we can understand the conductivity or many electrical properties of the semiconductor. So with the expression we are getting EF is equal to EC plus ED by 2 means the Fermi level lies in between EC and ED. Now we are going to find the density of electrons in the conduction band in extrinsic semiconductor. So for that we will be taking the expression for N first. So what did we have for N here? N is nothing but the concentration of electrons in the conduction band. N is equal to 2 into 2 pi ME KBT by h square power 3 by 2 e power minus of EC minus EF by KBT. You can also write it as, because the minus is if we have taken common. So if you multiply both the terms with minus, you can simply write it as e power EF minus EC by KBT. So this expression gives us the concentration of electrons in the conduction band. Now we are going to substitute the value of EF from equation 3. Whatever we have derived the expression for EF, we are going to substitute in this equation. So what is the expression we have now? I will write the expression here. 2 into 2 pi ME KBT by h square power 3 by 2 into e power EF minus EC by KBT. Now in this expression for N, we are going to substitute the formula for EF, whatever we have derived for EF at a temperature T. Okay, we are going to substitute. So what did we get for EF? EF is equal to EC plus ED by 2 plus KBT by 2 log ND upon 2 into 2 pi ME KBT by h square power 3 by 2. This is what we have got for EF. Now we are going to substitute this value of EF in this position. Okay, in the formula for N, concentration of electrons. So we are writing it as 2 into 2 pi ME KBT by h square power 3 by 2 exponential EC plus ED by 2, because for EF we are substituting the whole thing. All this is nothing but EF. So this is what we have taken. So EC plus ED by 2 plus KBT by 2 log ND by 2 into 2 pi ME KBT by h square power 3 by 2 minus EC we have here. Here we have minus EC. So we are writing minus EC upon KBT. Only thing we did is in place of EF we have put this expression. Now we are going to simplify it. How we are going to simplify? We know that exponential of A plus B will be equal to exponential of A into exponential of B, and also exponential of log x is simply x. So these two formula we are going to use here to simplify this. So how we are going to write now? 2 pi ME KBT by h square power 3 by 2 remains as it is. Now we are writing the exponential separately. So first we will have the exponential ED minus EC by 2 KBT we have. How did we get this? Here we have EC plus ED by 2, EC plus ED by 2 minus EC. I am just talking about this term and this term. So we have EC by 2 minus EC, 1 EC and half EC. So we will get ED by 2 minus EC by 2. Or you can simply write it as ED minus EC by 2. Because we are simplifying these terms now. For EC plus ED by 2 minus EC, we are going to get ED minus EC by 2. Now we are writing here ED minus EC by 2 KBT. And because we had logarithm of exponential ND power half upon 2 power half into 2 pi ME KBT by h square power 3 by 4. How we are getting this expression is, what we had is ND, we had KBT by 2 into ND by 2 into 2 pi ME KBT by h square power 3 by 2 we had. And when we have taken the log of exponential, we are left with this. You have exponential also and log also divided by KBT. So now this KBT and this KBT will get cancelled, and exponential and log will give us only this value with the power. Whatever we have here 1 by 2, it goes to the power. We can write it as power half. So we will get ND power half if I am having ND by 2 into 2 pi ME KBT by h square power 3 by 2. The whole thing we are getting half, because we are removing the log, because exponential of log x is giving us x. But this power for log, it can go to a power, log m will be m log a. So we have written it as power. So now ND power half we get, 2 power half we get, and 2 pi ME KBT by h square power 3 by 2 into 1 by 2. So we'll get 3 by 4. So we are writing the same expression here. Exponential ED minus EC by 2 KBT into ND power half by 2 power half into 2 pi ME KBT by h square power 3 by 4. Now how do we simplify this? Here you have 2. Here we have 2 power half. So 2 by 2 power half will give us 2 power half. No, we are having 2 by 2 power half. So if this goes to the numerator, minus half, 1 minus half is half. So it will give us 2 power half. And then here we have ND power half. Whatever is having power half, we are writing them together. So here we are getting 2, and also we have ND. Okay, so 2 ND power half. And then whatever value we have here, 2 pi ME KBT by h square power 3 by 2. And here 2 pi ME KBT by h square power 3 by 4. Suppose I have the numerator as x power 3 by 2 and the denominator I have x power 3 by 4. So how do I write it simply? Mathematics by 3 by 4. So this gives us x power 3 by 4. So what is our x here? X is this whole term. 2 pi me kbt by h square we are taking it as x. So what we are getting is x power 3 by 4 because in the numerator we have 3 by 2. Here in the denominator we have 3 by 4. So 3 by 2 minus 3 by 4 is giving us 3 by 4 in the numerator. So we are writing this is the term for x power 3 by 4 and the exponential term ed minus ec by 2 kbt. We are writing it as minus of ec minus ed. It is the same term. We are taking one minus common and writing it as ec minus ed by 2 kbt. So the same expression we are writing it as 2 nd power half 2 pi me kbt by h square power 3 by 4 into e power. You can write it as exponential or you can simply write it as e power minus of ec minus ed by 2 kbt. So this gives us the concentration of electrons in N-type extrinsic semiconductor. So for getting this, what did we do? We have first seen what is the concentration of electrons in the conduction band. And we have also seen the number of donor atoms that are added, the concentration of donor atoms Nd. And at lower temperatures, we are equating both N and also the Nd. The value we are getting, the concentration we are getting by adding Nd, the donor atoms, and we are equating, and after simplifying, what we get is 2 Nd power half 2 pi me kbt by h square power 3 by 2 e power minus ec minus ed by 2 kbt. So we will be discussing about the p-type semiconductor maybe in the next lecture. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.